don't see Stephen. Okay. We can copy here first, and I'll go through them. So the reason I put 4 of these up is because they tend to be confusing for students. So I wanted to deal with them right away. They're obviously all related, but they all mean something a little bit different. So an osmol, which is what we're dealing with osmolarity, with this big question that I'm giving you a homework for, is 1 mole of solute particles. Okay? Now what does that mean? Well, a mole of glucose and a mole of, for instance, sodium chloride are a little different in that glucose, right, which is a monosaccharide, is in its smallest form. So when you place glucose in water, it doesn't get any smaller. So if I place 50 millimolar of glucose in water, I'm going to also have 50 milliosmoles. It's a 1-to-1. But if I place 50 millimolar sodium chloride in water, I'm not going to get 50 milliosmoles. I'm going to get 100. That's because sodium chloride will dissociate, and you're going to get double the number of particles. Okay, so if the substance you're dealing with does not dissociate, then a mole and an osmole are the same, essentially. If the substance you're dealing with dissociates, then depending on how many pieces that substance dissociates into, you're going to have that many more osmolar than you do moles. Okay? That's the long and short of it. Osmosis is the movement of water, right? It is a special type of diffusion. So I've heard, if you've ever heard the term, I'm going to put the book under my pillow so that via osmosis I'll understand the information. What people really should be saying is via diffusion, because I highly doubt that water is going to get transferred from the book to your brain and vice versa. And I also highly doubt that any information is going to get transferred, but at least let's be correct. So osmosis is the movement of water. Osmolarity is the total concentration, right, and the units here of the solute. So osmoles per liter. So osmolarity is the equivalent to molarity, which is moles per liter, right? Total concentration. And osmotic pressure is a little confusing. Osmotic pressure, and I'll read this definition first and hopefully try to explain it. When a solution is separated from pure water, so you have to know what a solution is, what the 3 parts are, by a semi-permeable membrane, the pressure that must be applied to that solution to prevent water movement is the osmotic pressure. Right? Water would move down its concentration gradient to where the solution is. And the amount of pressure that you would have to apply to that water to prevent that movement is what osmotic pressure is. So essentially, the higher the osmolarity of a compartment, right, the higher the osmotic pressure that would have to be applied to prevent water from coming in. The more particles you have, the more pressure you have to apply to stop the water, and that's what osmotic pressure is. So you can actually measure this. Okay? So those are 4 relatively confusing when they're separated. I wanted to show you all 4 of them together. That way you could at least say, oh, okay, maybe it makes a little bit more sense. Maybe you're more confused. If you're more confused, we can talk about it. But that's the long and the short of that. Any questions on that? Okay. I think if somebody would lower the lights just a little bit, please, I'd appreciate it. So I think we ended here. Did we talk about clathrin-coated pits in this section? Okay. So these are 3 forms of endocytosis. There's actually more than 3 forms. Right? This is phagocytosis here. So this would be an immune cell like a macrophage, okay, that would engulf something. bacterium, it comes in via a phagosome, and then that phagosome will bind to a lysosome and it will destroy the bacteria. Okay. This doesn't happen in every cell. This only happens in certain cells. This is pinocytosis, also called fluid endocytosis. All cells do this, and it is a bulk way to move substances into the cell. And you can see that the substances are denoted by different shapes, whatever those substances are. So you can do it faster in some ways. It becomes a vesicle, and then that vesicle will go then to the nucleus, to the ER, to lysosomes, wherever. This type is clathrin-coated pit. It's receptor-mediated endocytosis. So an example for this would be cholesterol. Cholesterol uses this mechanism to get in the cell. So where would you find this mechanism? Well, you'd find it in your ovaries, you'd find it in the testes, you would find it in the adrenal glands. Anywhere where your body makes steroid hormones, this has to occur. Because cholesterol is the backbone, it is the skeleton for all steroid hormones. If you don't make or eat any cholesterol, you can't make estrogen, you can't make progesterone, you can't make cortisol, you can't make aldosterone, you can't make testosterone. Cholesterol, you have to have it. So if your diet is so low in cholesterol, your liver can actually make cholesterol. Okay? So the liver can make it. And we found out that cholesterol maybe isn't such a bad thing. We used to think that dietary cholesterol, the more cholesterol you ate, the higher your cholesterol went. Not true. It's not the way it works. Okay, but you need it. And if you can't make it with your liver, then you can't make these hormones, and it's going to severely affect your quality of life. Okay, so how does it work? Cholesterol in this case is a ligand. It binds to a receptor on the outside of these cells in these three different areas, right? If enough of the cholesterol molecules bind to the receptors, then those receptors will start to cause a pit here, an invagination. That pit then attracts clathrin proteins, and clathrin proteins form a net, okay? And it will pinch itself off, and then the clathrin-coated pit, the clathrin acts like a net to hold it together. Moves, and it moves from the membrane to what's called an endosome. An endosome is like a docking station area where you can then funnel things in different directions. So it's an organelle. You can then see that the receptors and the ligand, in this case cholesterol, are separated. The ligands go in the direction of the nucleus because cholesterol can affect nuclear transcription, right? The genetics are affected. And then the receptors are then recycled and reinserted back into the plasma membrane. So that's called receptor-mediated endocytosis. Cholesterol is an example of that. There are many examples of that. Now the weird thing about cholesterol is cholesterol actually doesn't require this mechanism at all. Cholesterol, because it's a hydrophobic molecule, can actually make its way through without this. This process speeds up the amount of cholesterol that can actually come through. Just like this, right? Some of these molecules here can make it through via a channel or a transporter. This actually just speeds up. It changes the amount that it can move, so the speed. So that is receptor-mediated endocytosis. So alternative functions, you should know this for endocytosis. You can transcellular transport. In other words, we're going to talk about transcellular transport, where you go from one side of the cell to another side of the cell. This is one form of transcellular transport. Endosomal processing, so you can change and process things. You can add proteins and carbohydrates, different types of chains. You can recycle the membrane. In other words, the membrane of your cell, there's data on this and how quickly your body and your organs recycle themselves every year. And certain parts of your body are being recycled on a daily basis, and certain every couple of months, and certain kinds every couple of years. For instance, connective tissue in tendons and ligaments actually take about 18 months to turn over. why they heal so slowly. And you can destroy engulfing materials. For instance, an immune cell, right? Like a macrophage or a neutrophil can use this. All right, this is talking about epithelial transport. For those of you who didn't take anatomy, or it's been a while, epithelial tissue is one of the four major types of tissue, right? There's epithelial tissue, there's connective tissue, there's neuronal tissue, and what else? Four types of tissues. Muscle. That's right. Okay. So, it is a type of tissue. It is all over your body. It lines organs. Okay? It lines organs and hollow areas. It lines your blood vessels, your GI tract. It is usually covering. There are different kinds. We're not going to go into them. All right. So, this is an epithelial cell. Here you have a lumen. The lumen side is the inside of a tube. Any tube. A hose, a blood vessel, your stomach, your intestine. So the lumen side, if this was your intestine, this would be where the food is. Then you have the epithelial tissue, and then you have the blood side, right? This is the interstitial fluid, and this is the plasma. So this is part of the extracellular fluid. All right, and these epithelial cells separate what's on the outside, technically, with what's on the inside. So what we're looking at here is transport. An example of transportation is, let's say this was in your GI tract, in your intestine, right? In your small intestine. There are channels in there that allow you to absorb sodium, right? And if this is moving in this direction, what that tells you, you don't even have me tell you, is that the concentration, the electrochemical gradient of sodium favors the arrow going in this direction. Now, once it gets into the epithelial cells, which is a transition state, then, since it's high out here and low in here, okay, and then you know it's high out here, remember, going back to that sheet, because this is the extracellular fluid, the only way that the sodium can now move from here to here is to have a pump, right? Primary active transport, right? Because here it's going downhill, and here it's going uphill. And so this happens to be a sodium potassium ATPase, which then pumps it out into the extracellular fluid. And so you can see what happens at the concentration. Concentration is high here, low here, high here. So this happens to be a diffusion, right? And this happens to be an active transport. Question? Okay. Another example, same thing. We'll use the small intestine, right, as this tube. So you have some secondary active transporters in the intestine too. It's really, really interesting. Not only can you absorb sodium, but you can absorb other molecules, for instance, like glucose, sugar. Okay, one of the types of transporters, so X can be glucose, it can be fructose, right? And they're going down their electrochemical gradients. Now, in the intestine, when you eat, this doesn't really apply because if you eat a lot of sugar, the gradient would be in this direction. So there are other tubes, meaning within here or within the kidneys, where, remember, this one is going downhill, this one has to be going uphill, or else it's not secondary active transport. And this is called co-secondary active transport. Now, once sodium comes into here, remember this is high, this is low, this is high. The sodium has to be moved out via primary active transport, but X, assuming it's high in here and low here, will just move down some kind of transport system. So it's facilitated transport, right? So you have facilitated transport, secondary active transport, facilitated transport with a transporter or a carrier, and then primary active transport, right? So the concentration here is high, low, and then high, meaning for the red, right? It's low here, it goes here. The only way it can go uphill is to use the motor. In this case, the motor is sodium. And then from here to here, it's high to low, so then it just goes down. It's electrochemical gradient. So these are just examples of things you've already talked another example. So there are things, again, this is in anatomy, we'll talk about this. So if you take an anatomy, we've already talked about this stuff. If you haven't, then you haven't, unfortunately. So epithelial cells, they form these types of junctions, all right? There are tight junctions. There are things called desmosomes. This is in your book, I think, in one of the earlier chapters. They talk about this. Desmosomes, there are adherens, there are gap junctions. And in this case, the junction is epithelial cells, and the junction is called a tight junction. And the tight junctions are always on the apical side. So we have to do some terminology here. When you're thinking about a cell, right, the top of the cell, or the cell that's facing the lumen, is called the apical side. The side that's down, usually, or away from that, is called the basolateral side. Okay, so the basal side and the apical side. The tight junctions are usually located on the apical side. They're generally designed to prevent water from moving very easily through between cells. So this is called paracellular transport. It's also people. Right? Now, if we were talking about this being your urinary system, right? Your urinary system, then in your bladder, right? Your bladder would have, and this is where the urine is, your bladder would have lots of these tight junctions, but in the bladder, these would be almost completely impervious to water. In this system here, it just prevents water from moving in very, very quickly. So there are different levels of tight junctions. The more tightly the tight junctions bind the cells, the less likely water is to move. Sometimes you're just trying to slow paracellular transport down. Sometimes you're trying to prevent it altogether. So more tight junctions equal more water resistance. So this is called paracellular transport. When you go from a lumen to an epithelial cell back to the extracellular fluid, and you go through a cell, this is called transcellular transport. So transcellular means you go through the cell. Para means around. You go around the cell. And that's what that is. So in this case, you have water using paracellular transport, sodium, and water here using transcellular transport. So there's lots of different variations to this theme. Okay? So you have to understand what that means, some of the terminology. All right. So there's a second part to this, and it's with the nervous system. So membrane potential, but we're going to come back to this. I have it inserted here because sometimes I talk about it early, but we're actually going to get to the nervous system. And when we do, I'm going to come back and use this plus the lecture there. So this is we're going to come back to this. Right? So now we're going to transition. I'm going to stop this recording. I'm going to transition to chapter 5. So we can stay on track. So just put a mark in your notes. If you put it down, the membrane potential, everything comes out here. I'm going to do this with the nervous system. Any questions on it? So let me transition us, because if I don't shut this thing down, actually, it may be able to do it. Let's see if it can. Because it's only taking a screenshot. I'm going to try something new and exciting here. Okay. So this picture here, and this is a picture I also use in my anatomy class, is a picture of, this is the inside of the cell, the cytosol, this is the outside of the cell. So this is intracellular, ICF, this is DCF. This complex here is called the glycocalyx. The glycocalyx is a combination of glycoproteins and glycolipids that form a barrier on the outside of the cell. These glycolipids and glycoproteins act as signaling molecules, so that they're kind of like a flag up in the air, saying, hey, come over here, here's where we're supposed to be. And they also act like a protective shield. They actually protect and make it more difficult for certain substances to actually get access to the actual plasma membrane. So that's a force field in some ways, at a very low level. Yep.
What was it called?
It's called the glycocalyx. I'll write it down for you. Glyco meaning sugar, calyx, outer portion. Okay, glycocalyx. So there are what are called glycoproteins, right? And these big green things represent protein, and these blue molecules here represent sugar. And then this is called a glycolipid. So in the plasma membrane, and again, if you haven't had any of this before, there is a chapter that talks about membranes and all that. It's actually done really, really well. It doesn't take very long to read it. But remember, this is a phospholipid bilayer. Out in this portion, there are phospholipid heads with these fatty acyl tails that has a backbone of glycerol. And then there are all these same types of heads on this side. So hydrophobic in the middle, hydrophilic on both sides. So this is the glycocalyx. It's a good thing to have, but it gets muckety-muck when you eat too much sugar. So if you're constantly eating sugar, you can actually screw the signaling process up so the cells don't work right. I'm talking lots of sugar. Not like you're eating normal. I mean lots and lots of candy. So that's the glycocalyx. So this chapter is about how the cells, and this is actually a cell biology chapter, right? We have an entire course dedicated to this cell biology. This is an introduction to cell biology. So for some of you to review, for some of you who've never seen it before, that's fine. We're going to get everybody on the same page. So how hormones and other signals work, chemical messengers. All right. So communication between the body parts requires signals or ligands. We gave an example of ligands, something that binds to a receptor, sodium, potassium, cholesterol, epinephrine, right? And a receptor, a binding protein. The chemical properties of a ligand predict its binding site. So if you took this in cell biology, they do something called binding kinetics. We're not going to do binding kinetics, Michaelis-Menten, that talks about what kind of an affinity these receptors have for the molecules that bind to them. Again, we're not doing Michaelis-Menten kinetics here. Some definitions: a hydrophobic substance is usually lipid soluble; it's fat soluble, right? So it's cytosolic or nuclear receptors. So there are types of receptors that are or lipid soluble. They're located in the cytosol or in the nucleus. All right, they tend not to be hydrophobic receptors. Tend not to be located in the outer membrane. Hydrophilic are lipid insoluble, and they're membrane-spanning receptors. So, for instance, I'll go right back here for a second. This might be a receptor. This might be a receptor. This might be a receptor. These would be types of hydrophilic receptors because there's water on the outside here. There's water on the inside here. Okay, so examples of molecules that are hydrophobic: steroid hormones and thyroid hormones. They're based on fatty molecules, lipids. Examples of substances that are hydrophilic: epinephrine and insulin. I mean, they like water. So something that's hydrophilic likes water. Something that's hydrophobic, phobia, has a fear of water. Question? Is everybody done right? Yeah. All right. So, and this is all in the notes, right? You have all this online. You can hear me talk about it. So I'll just read it. If you miss some of it, it's okay. Just try to get the big picture. You can always go back. Receptors are proteins that can bind only specific ligands. And so, for instance, you don't want an acetylcholine receptor, and we'll talk about what that is, not maybe today, but maybe today, to bind to an epinephrine receptor. Epinephrine is adrenaline. Okay, and adrenaline is going to get you jacked up. It's part of the fight or flight response. So you don't want different ligands binding to the wrong receptor, because if they activate that receptor, whatever happens downstream from that receptor could be bad or good. And so it's very, very specific. You only activate an epinephrine or an adrenaline receptor with epinephrine, and you only activate an acetylcholine receptor with acetylcholine. There's specificity, right? And there has to be. Or else you'd be all screwed up, right? You'd be doing things, when you want to go to sleep, you'd be awake, and when you want to be awake, you'd be asleep, and when you're angry, you should be passive. When you're passive, right, your hormones would be all screwed up. So there's a lot of specificity. Hydrophobic signals, kind of like estrogen, change genetic expression. So estrogen actually goes into the cell of the ovaries, okay, or wherever it's made from the ovaries, but whatever it's affecting, and actually changes gene expression. So, for instance, the best example of this would be Caitlyn Jenner, right? Bruce Jenner is transitioning to a woman. How does that happen? He's on hormones. He's on estrogen therapy, right? And so he's on estrogen therapy. He's taking so much estrogen that it's causing his cells to change. So he's developing breast. His skin is getting soft. His voice is starting to go higher pitched. He's losing hair where he had it, right? He's losing muscle. So his genes are actually coding for different proteins that are making him look more like a woman, right? It's a long-term process. The longer he stays on it and the higher the doses, the more like a woman he's going to look and act. So that is an example of gene expression, right? You do the same thing with a woman transitioning to a man. You start giving her testosterone, and she will eventually look and act more like a man. Chaz Bono would be the most famous of these people, son, daughter of Sonny and Cher. You know who those people are, or Cher's still alive, so people don't know who she is not. So he's an example of someone who's transitioned from a female to a male. His name is Chastity. He's a girl. He's a guy. He looks like a guy, a big guy. Okay. So hydrophilic signals typically activate rapid, short-lived responses. So, like insulin. Insulin's a fast response, right? You eat sugar, your pancreas releases insulin, boom, insulin goes up, tries to get that glucose out of the blood, and tries to lower your blood glucose very, very quickly back to normal. You don't want to have elevated glucose in your blood, sugar, for long periods of time. If you do, and if it's high enough, you're then called a diabetic, and everybody knows that diabetes is bad. I hope. Anybody think that diabetes is good? I didn't think so, but I had to ask. I don't know. All right. So again, don't worry about this. I'm not going to ask you to draw this thing, right? This is just what it would look like if we were looking at structural biology. It does show that there's an amine side, right, and a carboxyl side, and that there's a hormone binding site is in here. So that's really all there is. There's not much here. Okay. You should know these terms. Okay? I'm going to just come out and say you should memorize them only because then that's important, right? I'm saying to memorize it must be important. If you already know what these terms are, like anything else in my class, then you don't need to memorize them. But if these are really, really new to you, then a lot of the terminology I'm going to use, you're not going to understand the language. We have to be speaking the same language. So you have to have a different vocabulary. Talk about what a receptor is, specificity. I don't have time to go through all of this, but you should read through it. And if you don't understand something, then you should ask. All right? Because, again, I have competing interests in this class, and I can't go too slow and I can't go too fast. But these terms are really, really important in understanding what I'm actually talking about. And if you don't understand that, then you need to memorize this. Straight up, just memorize it, like everything else. So we'll just move on from here. But please ask. After you've looked at it, if you don't understand it, it'll be more meaningful for me to then explain it to you versus reading all of this. You all can read it. All right, so you have a cell. A secretory cell is a cell that produces something. Let's say that this is a cell that produces epinephrine, adrenaline. We use this as an example. Okay? Now, the chemical messenger here is a blue square. Notice that it has three options. Let's say there are three types of cells, there are three types of receptors. The blue square will only bind to the receptor that will fit the blue square, right? The blue square will not bind to this. This is an inverted triangle. This doesn't look like it. Everybody have that toy where you get blue and red thing where you put the shapes in, right? And then you open it up and the yellow pieces fall out. Same idea. Same idea. So you were learning about receptors and ligands and didn't even know it when you were 6 months old or older. Okay. Here is a different type of receptor. Whatever this thing is, you do not want it binding and activating these. So how do you prevent that? Well, you make them different shapes. Now, the dirty little secret is that this is nice. What you really have to do is you have to have an animation in order to really do this justice. In fact, this ligand and this receptor don't look alike until the ligand gets really, really close. In other words, this receptor may be just a flat rectangle. And as the correct ligand comes closer, it can notice, it understands what's getting near. This goes through what's called a conformational change. This is what's called, the process is called induced fit. Induced fit. In other words, it is tough to tell just by looking at the molecule when this molecule is near it that they actually go together. These three may actually look the same, except when this molecule gets to here, it doesn't change, it's not the right shape. And when this molecule gets here, it doesn't change, it's not the right shape. But when this molecule gets here, this changes and it is the right shape, and they bind and then something happens. So you get a response. So that's the induced fit model. And this is happening, all of these molecules here are in the plasma membrane. These are all hydrophilic receptors, meaning they're on the outside of the cell. They're not internal. So only cell A has the matching receptors for this chemical messenger, so it is the only one that responds. And you could have competing interests here, that these cells may be antagonists to one another. This one jacks the system up, this one turns it off. That would be bad, right? You turn it up, you turn it down. You turn it up, you turn it down. At the same time, you get nothing. It's not the way it works. Okay, cells B and C lack the matching receptors, therefore are not directly affected by the signal. And that's what we show. Any questions on that? Okay. This example is of a hydrophobic molecule. So we'll use testosterone as an example here. Testosterone is a steroid. It's an anabolic steroid. Okay? It is based on cholesterol. It is a hydrophobic molecule. Now, testosterone, when it is transported through your blood, is transported bound to a couple of things. Albumin is one of them, which is the most abundant protein in your blood. The other one is called sex hormone binding globulin. It also binds estrogen. Okay? So this green represents sex hormone binding globulin, and the M, we'll think of as male, represents testosterone. So the sex hormone binding globulin is actually a hydrophilic molecule, meaning it likes water. And so when steroid is bound to it, it can float through the blood and it's not going to clump up. You don't want fatty substances clumping up inside your blood vessels. That causes problems. Right? When testosterone gets to, let's say that this is a muscle cell. It's not. It doesn't look anything like a muscle cell. But we're going to pretend that it does, because a muscle cell looks like a tumor. But we're going to pretend. When the testosterone gets near a muscle cell, the testosterone will dissociate from the sex hormone binding globulin, and notice how it just moves through the plasma membrane. Why can testosterone move through the plasma membrane? What did I tell you about it? What do we know about hydrophobic molecules? What is the quality of the plasma membrane that allows a hydrophobic molecule to move through? Very important concept. What is that quality? lipid soluble. Inside the plasma membrane is actually lipid soluble. That's where the fatty acyl tails are, right? And so that is why a hydrophobic molecule can pass through. A hydrophilic molecule, like sodium or glucose, can't do this. So there's no receptor out here, it just floats through. When it floats through, it goes through the cytosol. Eventually, it will even transverse the nuclear envelope. And it gets inside the nucleus, right? That's where the DNA is, that's where your chromosomes are. It will then bind to a receptor that is inside. It's called a nuclear receptor because it's located inside the nucleus. That receptor and the testosterone bind the DNA, and they will turn on a switch, or a set of switches. And what it'll do is it'll become anabolic. It causes you to take on characteristics, male characteristics. It causes you to add more muscle, right? That's what testosterone does. It turns on the DNA. DNA, right, transcribes the message from, right, this is the central dogma of molecular biology. DNA goes to mRNA, to RNA goes to protein. So you transcribe from DNA to RNA, and then ultimately you make a protein, and that protein does something. So this is an example of a hydrophobic receptor system. The other example, well, we'll show you hydrophilics in a second. So an example of this would be testosterone. Estrogen works like this. Cortisol works like this. Aldosterone works like this. Progesterone works like this. DHEA works like this. Androstenedione. Anything that's a lipid-based T3 and T4, which are thyroid hormones, work like this. They all do the same process. So as long as you understand the process and you know what types of hormones do this, you get it. All right. So this is a hydrophobic signal. It requires a carrier protein modeled in plasma. Again, if testosterone was not bound to sex hormone binding globulin, and there is a small portion to this, so there's about as much of free testosterone, but it's teeny tiny, it would cause lots of problems with clumping. And what would happen if you start getting clumps in a blood vessel, like your arteries or your veins? What kinds of things start happening? Clumping inside a blood vessel. Heart attack, right? Heart attack, what else? Strokes. Right. Strokes and heart attacks, that would be bad, right? So there's a teeny tiny portion of these hydrophobic molecules that can flow in the blood, which is mainly water, but most of them have to be bound because, or else they cause problems. It's just the way they are. But then down here, but at the target cell, the signal moves easily through the membrane and binds to its receptor. And it moves easily through the membranes because it's hydrophobic molecule. These are all hydrophilic type receptor systems. In other words, all of these receptor systems are actually in the plasma membrane. Right? So where would that be here? So all of these receptor systems sit out here. This one is inside, internal, or in the cytosol, but these four sit in the plasma membrane. And you can see here's the phospholipid heads. Here's the two fatty acyl tails. You can't actually see the glycerol molecule. This is the phospholipid bilayer. Okay, so there are four messenger systems, main messenger systems, when you're talking about cell signaling. So I'll make sure that I have this open because sometimes I forget. All right. So there are four types. This is called an ion channel receptor. So attached to this receptor, and the first messenger here, we're going to talk about what a first messenger is and second messenger. The first messenger could be something like acetylcholine would be an example. Okay, so acetylcholine, you can abbreviate acetylcholine as follows. So if you're not a good speller, capital A, small c, small h. It's a neurotransmitter and a hormone. Acetylcholine binds to this receptor. It then opens up an ion channel. We're going to see this when we do skeletal muscle. This is actually called a nicotinic receptor. So there's a type of acetylcholine receptor that is called a nicotinic acetylcholine receptor. Anybody have any idea why it's called a nicotinic receptor? You ever hear that term nicotinic before, or something that sounds like it? It'll bind nicotine in cigarettes, chewing tobacco. Okay, so the acetylcholine binds to this receptor, and it opens up a set of ion channels. As long as this orange thing is bound to this, the ion channel opens, and then stuff will move down its electrochemical gradient, whatever that stuff is. And then you will have, now you have a first messenger. Because the first messenger is on the outside of the cell, you have to have a way to communicate what's going on here to the inside of the cell, and to the nucleus and to the DNA if you have to make changes. So then we have to have substances called second messengers. Right? Whereas here, you don't need a second messenger. Right? This is the first messenger right here, but it floats all the way through until it gets to the DNA. So the first messenger is all you need. But in this system, you're going to have a bunch of what are called second messengers. Right? This is kind of like the way they used to deliver mail in the United States. Everybody knows what the Pony Express was, right? You got a bunch of guys, gals, people, right? And you'd have mail come from, let's say, New York City. You got a horse and a guy, and depending on how much mail he or she could carry, and they would go, 20 miles. 20 miles from there, there'd be another horse with a guy. They would transfer, and they would keep playing this game until the packages in the mail got to where it wanted to go. This is the same idea. It's kind of like the Pony Express with messaging systems, right? It was going to keep handing off the message. It changes it. It changes the language slightly until it gets to where it needs to be. All right. So this is an ion-gated receptor channel. That's the first type. The second type here is called a tyrosine kinase receptor. An example of this would be the insulin receptor. Insulin works like this. Insulin would be the first messenger. It binds to the receptor. Tyrosine kinase is an enzyme. The enzyme catalyzes reactions and speeds the reaction up. It's got a tyrosine molecule on it, right? And that tyrosine molecule will actually bind this docking protein, and when this phosphate group binds to this, that's what this is, PO4, PI, phosphate, like an ATP, binds to the tyrosine kinase, there's a reaction that causes multiple steps, and you get a response. So in this case, the enzyme is actually attached to the receptor. Then there's another kind, the third kind here, is called the JAK kinase receptor. In this case, the kinase enzyme that does something is not attached to the receptor. This is actually part of the receptor, this isn't. So in this case, and an example of this would be cytokines. So I'll spell that for you. Cytokines work this way. Cytokine is a signaling molecule. If you've ever heard of cytokines, this is the type of messenger system that they use. So the cytokine binds to the first messenger. It activates a receptor. The receptor then activates the JAK kinase. Janus is actually named after the Roman god. Right? Janus is the equivalent of Zeus in Roman mythology. That's why we have January. Roman god, Janus. Okay. So it's a Janus kinase that activates the Janus kinase. And then a protein comes by when ATP is available. It has to be a special kind of protein. And it causes that protein and the phosphate to bind, which then activates this. So this would be a second messenger. And we're going to talk about this. And then you have a response. And then the fourth kind, right? And the fourth kind here is called a G protein couple receptor. And lots of them. Epinephrine uses this, serotonin, glutamate. So let's say glutamate, which is an excitatory neurotransmitter, it's also a hormone, binds to this. This is a G protein. It usually has three parts, a heterotrimeric meaning it has three parts. There's an alpha, a beta, and a gamma. Okay? When this binds, the alpha molecule will then attract GTP, which is guanosine triphosphate, which is just like ATP. The base is different, right? So it will attract GTP, and it will phosphorylate here, or dephosphorylate, and what will happen is the alpha molecule will dissociate from the beta and the gamma molecule and shift over. The alpha molecule now activates an effector protein somewhere else in the channel that's further away. That effector protein could be something like adenyl cyclase. Adenyl cyclase is an example. Alright? And this will generate a bunch of changes in second messenger. So these are the four major systems in the categories we're going to talk about. Each one of them I've given you an example for of a hormone or some kind of a molecule that uses each. Any questions on that? Okay. So this is the very first one. This is an ion-mediated channel. So in muscle, when we learn how skeletal muscle works, we're going to talk about the nicotinic acetylcholine receptor. It looks just like this. In that case, the ion that it allows to come through is sodium. So this is going to come back. So notice that in your syllabus, I call these sections the basics of physiology, right? There's a little bit of genetics in here, there's a little bit of cell biology, there's a little bit of chemistry, there's a little bit of physics. And I'm setting the stage so when we get to the actual systems, you're like, oh yeah, he talked about that. I get it. Now I know what he means by this receptor. If I don't set the stage, you're not going to know what the heck any of this means. All right. So in the case of a skeletal muscle, this is acetylcholine. It will bind to the receptor, and acetylcholine will open up sodium channels. So sodium will come in. All right, and that sodium is super important. We're going to talk about how it reignites the electrical charge. It starts the process over. That doesn't mean anything. And ultimately what happens is it causes the release of calcium because your muscles, anything that gets secreted or contracts in your body requires calcium. So your skeletal muscle cannot work without calcium. If you don't eat enough calcium, not a problem. It's just going to take it from where? Don't eat calcium. Where's it going to come from? Bones. You'll cause osteoporosis. That's why you get osteoporosis, because you don't eat enough calcium. The body needs calcium to do all these types of processes like move. Body says, okay, you don't want to eat calcium? No problem. I'm just going to strip it from your skeletal system until you fall apart and break a hip or break a bone, and so be it. That's more important than the structure of the system. If you bring in enough calcium throughout your life, you shouldn't break bones. It's as simple as that. And so this is an example. So this would be used in muscle contraction. So the binding of the ligand to the receptor alters the receptor shape, which then opens or closes the ion channel. So when this thing dissociates, the first messenger, the ligand, in this case acetylcholine, dissociates from here, the ion channel closes, and the sodium can't come in anymore. Does that make sense? Yes. For sure. Okay. All right, so there's the second one, right? Sort of the same idea. So each one of these I've already gone through. This is just a bigger version of that picture for you. Binding of the ligand to the receptor alters the receptor shape, which activates the enzyme function. Phosphorylation means it's a way of doing these second messenger systems. It involves kinases, and what it is there's a special kind of molecule called a kinase, right? And it's all it does really. It sounds very fancy, but it's right? It's not fancy. Kinases, all they do is they take a protein, right, and then they add a PO4 to it. They add a phosphate group. Sometimes we denote it, remember, because when we do ATP, we denote this. These two things are the same. PI and PO4 mean the same thing. So when I say phosphorylated, all I'm saying is that I'm adding one of these groups onto something, and it's usually an on switch. That process is usually an on switch for something. And it happens a lot, and it happens really, really fast. Okay, that's really important. Same thing here, binding the ligand to the receptor, alters the receptor shape, blah, blah, blah. Here's an example of where did you get the phosphate group to phosphorylate? You got it from ATP, and you added it to the protein. Now that protein does something. Until this phosphate group gets added to the protein can't do anything. Okay? So on, and so on, and so on. So here's just examples. You don't have to memorize this. Do not. This is biochemistry. Do not memorize this. I'm not going to ask you about structure. I could, but I won't. It's kind of pointless. Unless you're a biochemist, then you're a biochemist. That's not pointless. Okay, so you can read that. We'll start here next time. So, homework. That osmolarity sheet. The homework. Give it a shot. It's the osmolarity homework that I handed out. May I borrow that? It looks like this. There are 3 examples we're going to try. I'm going to tell you that you're going to need more than this amount of space to do these problems. Okay, so do it on a separate sheet. I want you to struggle with this. You know a little bit about osmosis. I want to see what you can do with this. Okay? I know it's going to be ugly. And then on Friday, I'm going to actually show you an answer. And then I'm going to put answers in e-learning so that you'll have what I would be calling a good answer eventually, and it'll be on e-learning. But I want you to struggle. Okay, so if you know someone who's done this, don't go to them unless you want to learn the process. But don't get to the answer, because I don't change these from year to year. The idea is for you to learn this process. Okay, so we'll do this on Friday. That's how we're going to start. Questions? Okay, great. Have a great day. If somebody would turn on the lights again, I'd appreciate it.